Hello everyone. Today my group are going to talk about our project, matrix factorization. The basic idea is there exists user rating matrix R, which is a very large matrix. Our goal is to find a matrix U, matrix V, which are smaller matrix that their product equals to the rating matrix R. What's more, we want the matrix U and matrix V contains some users and movies factors, such that we will combine the user factor and the movie factor. Then we will predict the outcome rating. The method one to do this factorization is PMF, probabilistic matrix factorization. Under this approach, we assume that the U and V, each column follows a multivariate normal distribution with mean vector 0 and a given covariance matrix with a hyperparameter. For this approach, we want to find the U and V that maximize the posterior probability, which is equivalent to minimize this expression to minimize this E. This could be done by gradient descent method. We just use gradient descent method on U and V. Then the U and V put into this equation, and the E will be getting smaller. After we get enough small E, we say that we found the desirable U and V as our prediction. But this method has several drawbacks. The first drawback is it needs human to control the complexity. More precisely, we need to control the recognition parameter lambda u and lambda v. The idea is there is a set of all appropriated lambda u and lambda v, but we don't know which one is the best. The thing we to do is we trained a lot of model, use each pair of lambda u and lambda v in the desirable set, then to find the best pairs. So you can see that this progress is very time costly. To overcome this drawback, we developed Bayesian PFM, which is the method we use. The idea for Bayesian PMF is we give those hyperparameters a period in each iteration. The hyperparameters can be updated by themselves based on our training data, so that there's no need for our humanly to control the complexity. It can be updated by themselves. More precisely, you can see on this equation. If you can sampling the UI and VI, then can calculate the probability. After sampling enough large UI and VI and take the average, we can approach the true value of the probability. That is the basic idea of Monte Carlo simulation. And luckily, we can sampling U and V by sampling UI and VI by a Markov chain, appropriate Markov chain. You see, UI just the columns of U, VI just the column of V, which are independently. So we just to draw n times UI and m times VI, then we can form the U and V. But the point is, the stationary distribution must be the posterior distribution. Another important point is, if we want to use MCMC, in this program we use GBIS sampling algorithm. If we want to use GBIS sampling algorithm, the most important point is we can be easily to draw the samples based on our posterior distribution. But luckily, you can do this in this problem. Because if we want to sample UI and VI, in this question, we just need to sample in the multivariate normal random variables. If we want to join the theta U and theta V, we just to join sample from Gaussian Weishart distribution random variables. And both random variables, normal and Gaussian Weishart normal random variables, those can be both sampled by MATLAB function that MATLAB provided. So we can easily sample the VI and UI, theta U and theta V, which means that we can implement the GBERS sampling algorithm. And the second point is, in theoretically, we need to burn some data because the previous samples on the Markov chain may not be drawn from the stationary distribution. In the previous Markov chain in each state, they may not be instantaneously. As long as we draw enough large samples on the Markov chain, such that we can guarantee that each samples are drawn from our posterior distribution. In our program, but in our practice, we'll omit this point. We now choose to burn some data, because if we want to create many GBERS samples, it's very time costly. So to reduce the time to make our program running faster, we omit this part, but theoretically it's needed. After we draw in the sample UI and VI, we can make a prediction. One prediction method is a hypothesis testing. In this problem, R is from 0.5 to 5, distant by 0.5. This is a discrete distribution. The thing we need to do is we can assume different rating R first and find the corresponding probability by UV samples. You can see this equation. After we get the samples of UI and VI, we can calculate the corresponding probability of RIG. After sampling, but the RIG is we assumed it first, such as we assume the RIG at 0.5, 0.1, 1.5, many. And for 0.5, we sampled many UI and VI and calculate the corresponding probability, take the average as the true probability. And repeat this step for R equals to 1, equals to 1.5, equals to 2. And finally, we find all estimated P and selected the biggest one as our prediction. But in our implement, this method is too time costly. We just make 10 iterations, then we need to take half an hour. If we want to take many iterations, like 100 times, 200 times, to make the outcome desirable, it takes a lot of time. But we believe if we sample many times, the outcome will be very good. So instead, we use method 2. We do approximation. Instead of assume different rating R and take the average, calculate the probability, take the average. After sampling UI and VI, we just use the production of UI and VI as our predicted R. Because for normal distribution, the mode is the mean. And we assume that the likelihood function follows the normal distribution, which mean is the product of UI and VI. So we just simply use the product UI and VI as our prediction. And sampling many UI and VI, make many prediction, make many production of UI and VI, and take average. Then we got the final R. R is the average of our sample, which are proven that get a very good outcome. After 200 iterations, the average RMSE is only 0.8. such that we can conclude that this approximation method works also well and works faster. That's all. Thank you. 录完了。